the punchline is that if pi has this Langland's parameter, well, I don't know, lambda bar, let me write lambda and nu. The bars are going to come back to annoy me now. So here I'm taking this nu to be in A star. This is the canonical representative. So I don't need a bar on the nu. Then this Hermitian dual of pi has a parameter lambda bar. This is exactly the same. And, well, I'll write nu Hermitian. This is the complex conjugate of nu. Well, what does that mean? There's a little bit of the complex conjugate of a complex linear functional is not a complex linear functional. So So the complex conjugate of a complex linear functional is not complex linear. So, well, so nu was an element of A star, which is Hom over C of A into C, and this is the picture in which it's not possible to take nu bar, but this is the same thing as Hom over R of A0, well, I'll write A of R into C. This is I said we could freely complexify representation theory. And this is the identification, the representation theory of A, A of R. And here, nu bar is defined. So this seems quite, this is a little bit peculiar. Well, one way to say it, nu bar means the map A to C defined by nu bar at some element of A is defined to be, if you take nu and evaluate it and take complex conjugate. So this sigma 0 is the complex conjugation, well, in A. So that's what I'm doing here. So it should feel like I'm taking something that's just obvious and making it really complicated. But it's, well, the claim is that it's worthwhile, that it's important to keep all these things straight. So, at any rate, that's what, well, this, sorry, that's what this means. It shows up here. Okay, so, excuse me. So, the conclusion well, again, here's this Langland's picture. This parameter, lambda bar nu, gives a standard representation. These have come up a fair amount, I of lambda bar nu. And this has a unique irreducible quotient representation that Langland called J of lambda nu, and this is the irreducible representation with Langland's parameter, this lambda bar nu. And excuse me. Well, I'm going to write quotient here. So, do this. The statement is that this Hermitian dual is that. And this J of lambda bar nu has an invariant Hermitian form. That's the same thing as saying that these parameters, lambda bar nu and lambda bar h nu, are conjugate. By what? Well, the cartan has not changed. It's the Weil group in G of R of H of R, and this is the same thing as the normalizer in K of H divided by AH intersection K. So, okay. So, that's
let's see. So on the previous point, you changed the new bar to new bar. New H.
right. Yeah, that's what new H means. Yeah, sorry. This.
So that's we have to change as well.
Yeah. That's what we're talking. That version of new.
So that's like actually the definition of new H.
Yes, that's right. That's right. Okay, so the easy case here is if nu is imaginary valued on this A of R, then, well, that's that's actually equivalent. This linear map being imaginary valued here, that's the same thing as these two being equal. So that's an easy way for these two things. These guys are conjugate by 1 in this. That's the easy case, and the so I'll record the theorem of basically Harishchandra and Langland's says that if this nu is purely imaginary, on this A of R, then this representation, well, I don't know, I'll write pi of lambda bar nu. It is, it's what's called tempered, which means that essentially it means it's part of the direct integral decomposition of L2 of G of R. And so it must be unitary. So these easiest Hermitian representations are unitary, and it's important that they're unitary. These are the ones that you need to do the most basic harmonic analysis problem, to decompose L2. And in fact, this is if and only if. Sorry? Yes. What's,
Well, I guess the big part.
it's, so the support of the direct integral decomposition of L2 is by definition a closed subset of the unitary dual, and that's, it means exactly that this belongs to that closed subset. So, and anyway, so these guys are easy. What's interesting, well, if I say easy, this just requires Harshchandra's harmonic analysis. So I want to fix the lambda bar, and you can define W of how do I write it? The file group in G of R of H of R. I can look at the stabilizer of lambda bar. Well, so it's the same thing as this normalizer in K of H divided by H intersection K. And so I mean, this is some subgroup of a Weil group. And let me take some elements in here. Then given this W, you get a family of Hermitian representations. So what I want to do is define A of R sub W. This is the -1 eigenspace of W on A of R. The W is any element of this Weil group that fixes lambda bar. And so this certainly acts on A of R. So for any such W, I can look at this -1 eigenspace, and then, well, these representations, J of lambda bar nu, for nu being in this, sorry. Well, I guess it's okay. So I'm ignoring, as usual, the imaginary direction. I'm only concentrating on real stuff.
Sorry, here, so W is actually background 干嘛？你那个你背的干嘛？To H start 干嘛
So,
I mean, where do the acts on the zero of base are embedded?
so let me, this lambda bar is, I can think of it as a character of this group. And so this normalizer in K of H, well, divided by H intersection K. Well, this is H over theta. Acts on those characters. So this vial group acts, it moves these lambda bars around, and I'm looking only at things that fix it, so this family of representations, this is a real vector space. And what this Atlas software does, it studies the signatures of these invariant Hermitian forms as as functions on these real vector spaces. That's the idea. And even, well,
I'm sorry for the meeting they are start. The stats, the group you open on.
yes. Sorry. Sorry. Yes. Sorry. Here I wanted just to use real values. Sorry. That's not what. Well, I guess the dual of a real vector space, I don't know, I've abused notation in many ways, but here this is a real vector space, and I'm talking about real linear functionals. Okay, so
David, I don't understand where this Atlas uses W.
it doesn't. But here's what matters. Well, sorry. So the question was, how does Atlas use W? So I think that there's a function like this is Hermitian for a parameter, and what this does is it takes a parameter lambda bar and nu. It takes the Hermitian dual, which is lambda bar minus nu. So where did I? Yeah. Then what it does is it decides whether this new parameter lambda bar minus nu is equivalent to lambda bar nu. This is the step where it's essentially looking for W. That's but it doesn't keep track of that W. It just says, does it exist or not?
It also doesn't actually define it new, but
Sorry, what's the comment?
Hermitian does something else when it goes in
Mark says that Hermitian is Hermitian doesn't replace nu by minus nu.
What it does may be equivalent. It tries to see what happens if you remove that.
It's hard for me to imagine what it could do that's somehow simpler than taking minus nu.
I'm not saying it's simpler.
Mark's always right.
I know, that's why I'm puzzled and not mad, yes. Okay. Anyway, so what matters is that this is the big idea that if this is true, then also that this lambda bar T nu is equivalent to lambda bar minus T nu for all, well, again, we only care about rational numbers. The issue is there some W that takes nu to minus nu and fixes this lambda bar? If there is, that same W will work for all multiples of nu. And the big idea is to look at this family of Hermitian forms. Well, I'll write this as, this is now a one parameter family of Hermitian forms on more or less the same vector space. And this is, I think, near enough gone. Not even close. And so the precise thing here is to study the signatures as a function of t. This is what Atlas does. And let me just, let's see. Look at a picture. Okay. I wanted to look at this picture. So, what's the picture about? These are representations of the split real group of type G2, and we're looking at the split Cartan subgroup, and so this picture well, we can say G is G2 sub S, I think. That's the